Hi, welcome to another video. Today I'm going to be looking at a byte and shifting left. How to do it and why is shifting left so useful. So to remind you, a byte are represented by these decimal values at the top here in yellow. I can't say they are always these decimal values because you get binary coded decimal and these higher bits would change. But a regular byte are represented by these decimal numbers. So bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, bit 1, bit 0. How do you remember what these decimal numbers are? Say in a year's time you want to go back to a byte. This is called 2's complement. Every number is the previous number multiplied by 2. So 1 multiplied by 2 is 2. 2 multiplied by 2 is 4. 4 multiplied by 2 is 8. 8 multiplied by 2 is 16. 16 multiplied by 2 is 32. 32 multiplied by 2 is 64. 64 multiplied by 2 is 128. If you add all of these numbers up together, you will have a total of 255. Therefore, a byte can hold a decimal value of up to 255. These lighter shade zeros are representing a number that I've defined as x, and x is currently set at 0. So I've no 128s, no 64s, no 32s, no 16, no 8, no 4, no 2 and no 1s. Hopefully that should make sense. Right, so now you can see I've changed x to 255. So that means bit 7 is now equal to 128. Bit 6, 64, bit 5, 4, 3, 2, 1, 0. But I don't want 128 here, or 64, or 32. I just want to know, is bit 7 set to 1? Yes or no? So convert this to binary. Now this is the total opposite to what this video is meant to be about. If I shift this bit 7 places to the right, it will become a 1. 1, 2, 3, 4, 5, 6, 7. So I'm effectively dividing bit 7 by 128. How do you work that out? If you work this way, shift it right 1 place, you're dividing it by 2. I've been through this on my shift right before. Shift it right 2 places, dividing by 4. Shift it right 3 places, dividing by 8. Shift it right 4 places, dividing it by 16. Shift it right 5 places, dividing it by 32. Shift it right 6 places, you're dividing it by 64. Shift it right 7 places, you're dividing it by 128. So if bit 7 is 128 and I'm dividing it by 128, I will have a 1 here. And similarly with bit 6, shift it right 6 places. And in bit 5, shift it right 5 places. Bit 4, shift it right 4 places. Bit 3, 3 places. 2, 2 places. Bit 1, shift once, divides by 2, you can see. And bit 1, no need to shift it. I'll do a screen capture of the code as we are at the moment. I've defined this number as bit 7, which is hexadecimal 80. Bit 6 is hexadecimal 40, hexadecimal 20, 10, then 8, 4, 2 and 1. And if you're wondering about hexadecimal, you haven't watched my hexadecimal video. You can see I've now changed these lighter character numbers to a binary representation of x. So x is still 255, and you can see we've got one of those, one of them, one of them, one of them, so on and so forth. Now let's move to shifting left. So I've made x equal to 70. So 70 in binary equals a 64 plus a 4 plus a 2. Add those three numbers up, equals 70. But let's say I want to step up through the byte to see which bit is on. I can write the number here and include an AND with a function that steps up through the byte. So in this case I've chosen I. So this will write the number X and I. And the AND I will return a 1 if the bit is 1. So here, for example, this bit is 0, so the AND I will give me a nothing. Nothing, nothing, that will give me a 1, that will give me a 1. But then to keep track on where we are in the byte, I've got another number here just to represent these decimal values. So we know if we're at bit 0 or bit 7, so on and so forth. Now this function is running at the moment, but we see nothing happening. Let me show you the code. Right, here is my code. So quick rundown, all these bits are the hexadecimal values of X. So the most significant bit, hexadecimal 80, 40, 20, 10, 8, 4, 2, 1. When I write the number, I'm shifting it right as described. So bit 7, shifting it 7. So if bit 7 is equal to 128, I will see a 1. If bit 6 is equal to 64, shifting it 6, I will see a 1 or a nothing. Here I'll see a 1 or a nothing, 1 or a nothing, so on and so forth. Then I'll write the number X and I. So the AND, the ampersand I, will return a 1 if the bit I'm looking at is 1 or greater. If it's a 0, it will return nothing. So to step up through the byte, I want to look at the number and I. So you saw the screen was static, wasn't doing anything. It showed our binary representation of 70, and that's it. Nothing was happening. Why is that? I equals I multiplied by 2, which is the same as shifting left one place. Have a look at the I equals nothing. Nothing multiplied by 2 is nothing. Nothing multiplied by 4 is nothing. Nothing multiplied by any number is still nothing. So here you cannot shift up through any byte because I equals nothing. And that's what I was saying, it's a classic mistake. Make I equal 1. Now all of a sudden we will look at bit 0, 900 millisecond delay, then we I equals I multiplied by 2, or I equals I shifted left one place. Same as multiplying by 2. 1 multiplied by 2 is 2, shows the number, then comes back round in a loop. I equals I multiplied by 4, then 8, then 16, 32, 64, so on and so forth. Let me program this and I'll show you. Here we are. So changing the I from a 0 to a 1, it's now stepping up through the byte. These are our decimal places in yellow, and you can see the red is representing the place where I is. So we had X defined as 70. So you can see this is our I counting, and when it returns a 1, we get the value here. 0, 1, so when it's at bit 1, it's returning a 2. So we know 2 has the bit set. When it gets to bit 0, 1, 2, it's returning a 4, so we know that bit is set. And then when it gets to bit 6, it's returning a 64, so we know that bit is set. And all the other bits are 0. So all I simply do, this is looking at X, which is defined as 70, I can just get it to look at a byte in a font array and step through every single bit of every single byte in the font array. Now some of these characters might only be 99 bytes long. The large font I left you with the other day was 1300 bytes long per character. And to get these numbers and pixels on the screen, I need to know which bit of the byte is equal to a pixel. A 1 is a pixel, a 0 is a background colour. So this is taking a number, joining it with an ampersand I, shifting left through the byte and displaying our number here. So starting with bit 0, 1, 2, 3, 4, 5, 6, 7. Remember to look at the positions up here. 0, 1, 2, 3, 4, 5, 6, 7. And we are taking that 1 and multiplying it. We are taking the 1 and multiplying it by 2, which equals 2. We are in that position. We are then multiplying 2 by 2 equals 4. Multiplying 4 by 2 equals 8. And that's how we step up through the byte. Step up by shifting left, step down by shifting right. Left, you multiply by 2 each time you shift left. If you shift right, you are dividing by 2 every time you shift right. Hopefully you now understand shifting left through a byte and joining your number with an ampersand to get the bits you want. Thanks for watching.